So in this lecture, we are going to continue to build upon what we talked about last time. So let me just give you a quick recap of what we talked about. So we said that the luminosity, its symbol is L. So this is simply the total power of radiation emitted by a star. And why are we talking about radiation? We also discussed this because a star does not just emit light, right? It emits a continuous frequency of wavelengths, right? Sorry, a continuous spectrum of wavelengths, and we'll talk about that in the lectures to come as well. So since light is not the only type of radiation emitted, to generalize this to all the types of radiation, we instead use the word radiation, right? So luminosity is the total power of radiation emitted by a star. And then we also talked about the radiant flux intensity, right? So this is also called apparent brightness. So this is actually a measure of the brightness that we see on Earth of any star, no matter what its distance is from us, right? So this is the radiation, or we should say the power of radiation of a star incident per unit area when arriving normally to the surface, right? So normal means perpendicular. At a surface, right? So we talked about this last time. We also saw one formula. So the formula which links luminosity and radiant flux intensity is this one, right? F equals L upon 4 pi d square. This is all you need to know for your exam, right? So the definition, this is usually asked for 1 marks in your exams, and the usage of this is also expected. So last time we talked about so with reference to the questions we posed right at the start of the unit, so we know that measuring the brightness of the stars, that was one of our focal questions, right? So one of the most important questions we had to talk about. So that is really F, and how we measure this is using telescopes, right? So we have, and what astronomers have been doing for the last 100 years or so, is that they have been majorly perfecting how well can a telescope measure the intensity, right, that brightness of a star, right? So this is how we get F. And how we actually get the distances of these stars is that if we know the luminosity of a star, right, so then we can calculate this pretty easily, right? Then we just have to do some math, make D the subject of this equation. But the real question is, how do we get the luminosity of a star? So at this point we are going to talk about what the title written above was. So in astronomy and cosmology, such objects are of great use to us, are of great importance to us, which are called standard candles. And these simply refers to objects of which you know the luminosity, right? So objects for which you know what the luminosity exactly is, that is a standard candle. So this is also asked often in your exams. So standard candles are objects of known luminosities. Right, so once you know the luminosity of a standard candle, then using this formula you can just rearrange this to find the distance of that standard candle from Earth as well. Right, so majorly there are two types of standard candles, and these are not really part of your syllabus, but let me just go through them because this can be asked in a question. So it's better if you have some knowledge of this beforehand as well, to just help you tackle that question better. So one of these standard candles are called Cepheid variables. Right, that's how you pronounce it, Cepheid. So the special things about these stars are that their luminosity varies periodically with time. Right, so unlike the star, for example, if we talk about the star, so we'll see that the star has the same brightness always whenever we can see it, right? So the stars, this brightness of the sun, for example, is not changing. But unlike the sun, a Cepheid variable is really a star which has a luminosity which is varying periodically with time. So this was discovered first by an American physicist called Henrietta Leavitt. And another thing that she discovered about the Cepheid variables is that more luminous objects, right? So stars, so these Cepheid variables, so the ones that were more luminous, right? The ones that appeared more bright, they also had a greater period of variation. So now at the end of A2 we obviously know what periodic means. So this luminosity, this brightness is changing periodically. What this means is that after a certain time it has the same brightness again, right? And let me just show you an example of this. So this star is a Cepheid variable and it's in our Milky Way galaxy. So this star is actually called RS Puppis. Right, I don't know who came up with these names, but this is one of the brightest Cepheid stars in our Milky Way galaxy, and this is very, very bright, and this has a period of almost 41.5 days. Right, this is not for you to remember, this is just so that you can actually understand what we are studying here. So this is very bright, so this has a large period. In contrast, a less bright star would have a smaller period, right? So just like how we would do for a normal P5 questions, what Henrietta did was that she simply plotted a graph of the luminosity versus the period, and she got a straight line like this. So she inferred that there is some sort of a straight line relationship. So not exactly linear because this isn't passing through the origin, but this is somewhat of a relationship that she was able to deduce. So if we can, so by observation of a star, if we can measure, we can obviously measure their period. So then we can just go on to this graph and extrapolate to find its luminosity as well. So maybe somewhere here, right? So this is how log axis works. Not really required for you to learn, but the value in the middle is not their midpoint. So this value in the middle is actually 31.6. So using this graph, we can then deduce its luminosity. Right, so if you also Google this, you'll find that the luminosity of RS Puppis is more than 10 to the 4 watts. Right, so this is how we use Cepheid variables to find the distances from the Earth. Now let's have a look at one of the questions which goes over the same concept. So let's have a look at this question. So what this question says is the luminosity L of a Cepheid variable is estimated from its period to be 4.6 into 10 to the 15. So this is exactly the type of question you would get in your exams. You are not required to know how you get the luminosity of a Cepheid variable from its period, right? Its radiant flux intensity, right? So we know this is small capital F. So this is measured on Earth as 1.3 into 10 to the negative 23. This is L. So if we want to find the distance, we simply use this relationship that F, the radiant flux intensity, is given by this expression, L upon 4 pi d square. Right, so let's just check out the units. So this is in watts. This is in watts per meter square, so pretty much standard units. So F is so F is 1.3 into 10 to the negative 23. L is 4.6 into 10 to the 15. and you have 4 pi d square here. So if you want to find out d, which is the distance, so d square would be 4.6 into 10 to the 15 upon 4 pi into 1.3 into 10 to the negative 23. Right, so just plug these numbers into your calculator and d square turns out to be, oh, so this was supposed to be 10 to the 15. So d square turns out to be 2.82 into 10 to the 37. Obviously, I'm going to give my answer in 2SF because that's the number of least significant figures I have. So taking the square root on both sides, d, the distance, turns out to be 5.3 into 10 to the 18 meters. Right, so that is how you calculate the distance of any standard candle from Earth. Right, so when we say a standard candle, it's obvious and it's implied that we know its luminosity L. F can be known by the telescope. So if we know F and L, we can just rearrange this equation to find D. So there are some other types of standard candles as well. So you also have something called a supernova. Right, so a supernova is also a standard candle because you can calculate, you can measure its luminosity. Right, so once you know the luminosity, you can also calculate the distance of this supernova from Earth. Right, so what is a supernova? Basically, it's a really cool explosion that happens, and in so many words, it is just the death of a star. Right, so when a star dies out, it explodes, and that has a huge luminosity. So kind of just like an estimate, so the luminosity of a supernova, so the luminosity is approximately 10 to the 36 watts. Right, so this luminosity is approximately 10 to the 36 watts. So if you remember the figure for the luminosity of the sun, that was 10 to the 26. So that is, so the luminosity of a supernova is 10 to the 10 times as 10 to the 10 times greater than the luminosity of the sun. Right, and again you could have the same question like the one we did above, but for a supernova, and the method would be the same. So let's have a look at this question now. So a supernova is a star that explodes and outshines its host galaxy before it fades away. In 2014, a supernova event occurred in a distant galaxy. Its luminosity peaked at about 4.4 into 10 to the 36. So we know this variable, this value corresponds to L, right? This is luminosity. The maximum radiant flux intensity at the Earth from the supernova was 0.21. So we know this is F. And you can also double check with the units. So power upon area. So this has to be the radiant flux intensity. Estimate the distance. So what we would simply do is we would again use this formula, F equals L upon 4 pi d square. So F, the radiant flux intensity, is 0.21 pico. So pico is 10 to the negative 12. Right? L is 4.4 into 10 to the 36 upon 4 pi d square. So you can just rearrange this equation to find out d. Right, so this would be 4.4 into 10 to the 36 upon 4 pi times 0.21 into 10 to the negative 12, and this would also be under the root. So from here you can calculate d as, so this turns out to be 1.29 into 10 to the 24. So just to 2SF, this would be 1.3 into 10 to the 24 meters. Right, so because if we talk about Cepheid variables, they have a less luminosity, so they can only give us so much distances, but supernovas, being much more brighter, can actually enable us to find much larger distances. Right, so that's the end of this video. In the next one, we'll be going on to some more concepts related to some of the laws that actually enable us to find out more information about such luminous bodies. So stay tuned and see you there.